Our topic is moving charges and magnetism. We'll understand what is magnetism due to a moving charge. Later on, we'll dig deep into this topic and we'll understand materials which are magnetic and materials which are not magnetic. So we'll study them later on. Now, we have already discussed and you have already solved so many problems. If we have a static charge, I'm using the term static, that is a charge which is not in motion. So a static charge of, let's say, the charge is plus q. What it does? It creates an electric field in its surrounding. This is, we know, and that electric field is, these are equipotential surfaces. Electric field actually decreases with the distance as you move forward. So if this is our charge and let's say we are talking of this point in space which is r distant from this charge, then what we say or what we conclude that the electric field intensity at this point P due to charge Q will be equal to 1 by 4 pi epsilon 0 Q by r square. And if the position vector here is unit vector is r cap, our electric field is a vector quantity which is given like this. This you know, we have already discussed these things. What is the meaning of electric field? Is it just a fiction? No. It is in the vicinity of this charge, where if another charge is brought, that charge will experience an electric force. Not only that charge, this charge will also experience an electric force because of that charge. But let's say we have somehow clamped it to this point. Then if another charge, let's say Q1, is brought to this point, okay, which is also, let's say on the, the length is also r. What you'll get that the electric force between these two charges is QE, or which we know as Coulomb's law, 4 pi epsilon 0 Q1 r square. Clear? This we have studied. Now, what is magnetism then? We are talking of electric force and we are talking of electric field. What is magnetic field? Like a static charge, as a static charge produces an electric field, similarly, a charge, let's say Q, moving in certain direction with a velocity v, that is to say, if a conductor is carrying a current I, what is happening? We have several charges moving in a particular direction. So if let's talk of single charge, if a charge moves in certain direction with velocity v, or a current is flowing in a conductor, same thing, charge is crossing, this produces magnetic field, which is given as B. We write electric field as E, this is given as B. It is similar to electric field. The only difference is a static charge produces an electric field, but when the charge is moving along with the electric field, it also produces magnetic field. Don't get confused that once it starts moving, it won't create electric field, it will create only magnetic field. No. This moving charge will create electric field and it will also create magnetic field. Clear? But when the velocity is 0, that is when it becomes static, it produces only electric field. Okay? Now, I told you that because of the charge, the electric field is QE. Let's say this is electric, this is the electric force. Due to a moving charge, we have another force, that is, let's say Fm, magnetic force, which is given as Q, V, that is velocity, cross B. This is cross product, V cross B. This is, the force is V cross B. That is, if we have, let's say, this is your electric field, E, and let the magnetic field be this. You understand this sign? This sign means arrow, inside. And if you have this, this means up. The arrow is coming out. And this is in this direction. So I am, for the time being, let this be the direction of magnetic field. Or, let's say, the direction is like this of magnetic field. Let there be a distance. I'll explain to you what is the direction of the force. For the time being, just try to understand, if we have both electric and magnetic field and we have a charge q with velocity v in this electromagnetic field, that is combination of electric and magnetic field, this charge will experience an electric field which is equal to QE, and this charge will experience a magnetic field which is QV cross B. Therefore, the total force on this charge, a charge entering an electromagnetic field, will be Fe, that is due to electric field, plus Fm, and this, you know, this is a vector addition. So this becomes QE plus QV cross B. Okay, so this is a very important result, a very important expression. This force is called Lorentz force. Okay, that is the Lorentz force is the force due to the electric field and magnetic field combined. Clear? Now let's understand what is the direction of the force due to magnetic field. Let this be our magnetic field, that is, this be the direction of magnetic field, and our velocity is in this direction, the charge is moving in this direction. This is V cross B. You know what is V cross B? It is cross product. V cross B means, let's say this is the direction of V and this is the direction of B. We use simple screw rule or right hand thumb rule to understand the direction. What is a screw rule? You will take V cross B. This is first. So V here and B here. So this will, if you go from V to B, this is the direction. This will be the direction. So this is what? Clockwise. So if you know how a screw is, actually we have screwed this board onto the wall. If you apply a screwdriver in anti-clockwise direction, the screw will come out. And if you apply the screwdriver in clockwise direction, the screw will enter inside. So this is clockwise. Clockwise means into. That is, the direction will be like this. That you will see the back of the screw. It will get inside the back of the arrow. But if the case is like this, let's say this is B and this is V. So now V cross B is this. That is anti-clockwise. So it will come out. So the direction will be this. Okay. I think direction clear. Now by right hand thumb rule, see what we do. V cross B, we wrap our fingers like this. So V cross B is wrapping like this. Where does the thumb points? It points into the wall. So this is the direction. Here, see V cross B like this. Thumb is pointing out of this wall. So this is the direction. This you should understand. This will be QVB sine theta if there is the angle between the two is theta, and V cross B means VB sine theta. Okay, so this is Lorentz force and this is direction of the force experienced by a charge due to electric and magnetic field. Now, we know that electric field obeys the law of superposition. That is, if we have several electric fields, E1, E2, E3, E4, they are added. The net electric field will be algebraic vector sum of all the electric fields. That is, if the net electric field is E1 plus E2 plus E3 and so on. That is, if we have several electric fields in an area, let's say this is E1, this is E2, this is E3, like this. So this is law of superposition. Similarly, if we have several magnetic fields, let's say this is B1, this is B2, this is B3, what will be the net magnetic field? It will be this B1 plus B2 plus B3. So magnetic field also obeys the law of superposition. Now what is the unit of magnetic field? This is your next question. Unit of magnetic field. See, F is QVB. That is, Q will be in coulombs. If you take, just try to understand what is the unit. Coulombs, velocity will be meter per second, and this is B, and force is what? Newton. Force is given in Newton. So what do you get for magnetic field? Magnetic field is Newton seconds coulombs meter. Okay, you can find out the dimensions also in MLT. Now how you can get, because Newton will be ML T minus 2, charge will have something, V will be something, so you can get that thing. Now let's understand what is the SI unit. This in SI is called Tesla, T, after the name of the scientist Nikola Tesla. Okay, so this is Tesla, but Tesla is a very big quantity, because if you say what is the magnetic field at the surface of Earth, it is roughly around 10 to the power minus 5 Tesla. So a non SI unit, that is Gauss, is often used, which is actually equal to 10 to the power minus 4 Tesla. So many a times you will find that the magnetic field is, let's say, 3 Gauss. So you should understand, you'll have to convert it to SI unit, that will be 3 into 10 to the power minus 4 Tesla. Okay. Now our next topic, what is the magnetic force due to a current carrying conductor? Okay. So let's see. Let's say our conductor is like this. Okay. Let its cross-sectional area be A. Let its length be L. LA. Let N be the number of mobile charges per unit volume. Okay. Let N be, that is, in a particular volume you have N number of charges. So the complete volume is A into L. So NLA will be the total number of charge. Okay. Let VD be the drift velocity. Drift velocity, you know what is? The average velocity with which the charges are moving. Okay. So let this be the case. Then you know F is what? F is given as Q V cross B. Clear? So what will be Q here? If the charge Q is, if we have one charge equal to Q here, let's say this is one charge. So total number of charges is N into L into A into Q. Why? Because N is density, mobile charge density, into volume. This will be total number of charges into Q. Okay, and then VD cross B. Okay. Now look at this carefully. This is volume. If you just take it out and you have NQVD, let us take LA out. What is this? Volume charge density, sorry, charge density, yeah, volume charge density into charge into velocity. This is current density. If you remember, we have used it, we have explained it in our video on charge density. So this is basically, we denote it by J. So this is J cross B. Okay. Now if you multiply A into J, current density into A, what you get? You get current. So what you will get is J into A, this will be I, and L will be, actually this vector will transfer to this part and you will get L cross B. L is the direction of the length. Okay. So this is a very important relation. This is force due to a current carrying conductor. That is, if a current carrying conductor is placed in a magnetic field B, let this be this. If it is placed in a magnetic field B, what will be the force experienced by this conductor? This is I L cross B. Okay. Now from here, let's talk of this V cross B. What do you understand by this? V cross B means VB sine theta. This you know. That is the angle between velocity. If this is charge, velocity, if charge is moving with velocity V and the magnetic field is, let's say, this B. So this is theta. So this is VB sine theta. That is, if velocity and magnetic field are parallel. That is, if the direction of B is this and direction of B is also this, or reverse to it, parallel or anti-parallel, theta will be 0, then your magnetic field will be 0. Where it will be maximum? It will be maximum when theta is 90 degree. That is, if velocity is this, then either it is this or it is this, then only this magnetic force will be maximum. Similarly here, L cross B. So if L and B are in same direction, then if force experienced by this conductor will be 0. But if it is 90 degree, L and B are 90 degree, like this, L is this and this is 90 degree to this magnetic field, then it will experience maximum force. Okay, let's solve a simple example to understand this. Now our question is, we have a current carrying conductor, let's say AC, which has a length of 1.5 meter. L is 1.5 meter. The mass of this conductor is 200 grams. It is suspended by a magnetic field horizontally. That is, this is in air, mid-air, suspended. We have a magnetic field in this direction which is holding this conductor. We have to find what is this B when the length of the conductor, mass of the conductor and current in the conductor is given. See, it's very simple. We'll have a free body diagram. This side we have mg and this side we have magnetic force due to magnetic field. This magnetic field, we are ignoring magnetic field due to earth and all. So this is free body diagram. That is, Fm will be equal to mg. And what is Fm? Fm is I L cross B, but this is 90 degrees. So L cross B becomes LB. Why? LB sine theta. Theta is 90. So LB M into G. So we have this value, we have to find this. So B, M is 200. This is, sorry, not 200, 200 grams. So it will be 0.2. We will be taking everything in SI. So 0.2 into 9.8 by I. I is 2 cross L. L is 1.5. See, this is 10. So let's get the value of 9.8 by 10 into 1.5. That is 15. 9.8 by 15. So this is 0.65 Tesla. Okay, and you know the direction. Obviously, if this was in this direction, it wouldn't be possible for it to hold this force. We need magnetic force due to this magnetic field in upward direction. Then only you can hold this weight. Okay.